Hello and welcome back to linear regression using R, part 2. In part 1 we learned how to fit a linear regression model with one response and one explanatory variable. Today we're going to introduce more than one explanatory variable plus interactions, so it's going to get a bit more complicated now. As you can see, I've already opened R here. The console window is on the right hand side and the editor window on the left hand side. I've already loaded also the air quality dataset using the data command, and we can see the names of this dataset here in the editor window. First of all, let's start with a plot of the variables that we're interested in. So we start with a plot of ozone versus solar radiation, and our dataset is the air quality dataset. Okay, there you go. You should know this graph already from the last video. So let's produce the next one. This will be a plot of ozone against the wind speed, and you can see there is a negative relationship here. Might be nonlinear, might be linear. We don't care about nonlinearity today, but we want to model the joint influence of these two variables on ozone. We want to model the joint influence of solar radiation and wind on ozone concentration. As usual, I proceed by annotating my script here, so I say produce plots of explanatory variables, or let's say for some explanatory variables. Alright, so we've looked at these plots. We can see and we already expect that one of these variables is positively related to ozone and the other one will have a negative effect. Alright, so far so good looking graphically at these variables. What we would like to do now is to look at the joint influence of both of them. The easiest way to do this is to use the coplot command, which allows us to simultaneously plot more than one explanatory variable and their effects on a response variable. So we put in ozone as the response here, which will be plotted on the y-axis. And let's just say we're interested first in solar radiation, and then we are additionally interested in the effect of wind. So we use this vertical bar here to state that we want to plot the relationship among ozone and solar radiation conditioned on wind here. And we also want to have some scatter plot smoothers added to this plot. So we use the panel equals panel.smooth. If we do that, nothing will happen. So we have to tell R again that the air quality dataset shall be used. And you can see in a second what's happening now. So this is the coplot, and this takes some time to get used to. So what do we see here? We see the solar radiation on the x-axis and ozone on the y-axis. And then we have 6 panels here. 1, 2, 3, 4, 5, 6. 6 panels showing local regression fits. And the first panel down here is for low wind speed, as indicated by this bar up here. So we have a strong relationship, strong positive relationship among ozone and solar radiation for low wind speed. And you can see that this relationship levels off the higher the wind speed gets, which is also not so surprising given that wind will blow away the air and the ozone contained within it. So the relationship between solar radiation at a given point and ozone concentration will just be reduced when we increase the speed of wind. So once again, we read these panels from bottom left to top right. So 1, 2, 3, 4, 5, 6. And this also corresponds to the classes shown above here, 1, 2, 3, 4, 5, 6. So you can see very easily now already that there might be an interaction between wind and solar radiation and their effects on ozone. So let's close this graph and use LM in order to produce our regression model and interpret it. Call it model 2 because in the last video we already had model 1 here. Model 2 gets LM Ozone Solar.R times wind. Data equals air quality. So what does this model do now? We have ozone as a response variable. The tilde symbol here just says is modeled as a function of, and then comes solar radiation times wind. This means that we fit solar radiation plus wind plus the interaction among solar radiation and wind. Alright, let's do that and let's directly interpret the model. Before we do that, we plot it as usual, and we focus on the plots number 1 and 2 that appear now. Okay, there you go. You have to click somewhere now in the graphics window on a Windows system. So this shows there is pattern in the residuals. We should not trust this model too much. There is some indication of nonlinearity, and there is some indication of variance heterogeneity in here. So the model will have to be improved further later on. We don't care about it now, but I just want to tell you that this residual plot should raise eyebrows, and we need to do something against this. The QQ norm plot, as in the last video, shows that the residuals are clearly not normally distributed, so both the very negative and the very positive deviations show also deviations from normality. We close all these windows now. We know that the model potentially isn't perfect yet, but for today we keep it as it was, because the aim of this video is to show the principles of multiple regression, and we'll improve this model further in the next videos. So we use summary model 2, and here we see the following output now. We see the intercept. The intercept is 34 in the units of ozone concentration, and the intercept is the value of ozone concentration for 0 solar radiation and 0 wind speed. So this intercept is not really of interest for us. We will see later on in future videos how this intercept can be made better interpretable using centered explanatory variables. For now we keep it as it is and move on to the next 2 lines, which state the relationships among solar radiation and ozone. But there's a but here. We have the interaction term down here. Because this interaction term is here, the main effects of solar radiation and wind are conditional effects. So this solar radiation effect here is conditioned on 0 wind speed. So only for 0 wind speed the relationship between ozone and solar radiation is positive. Likewise, for this effect of wind here, we can see it's negative, but only for the case of 0 solar radiation. And this interaction term here has a negative coefficient, and we will see that this is difficult to interpret from this numerical output here. So the best way to proceed is to try to see what the model did graphically. Let's try out the termplot function that we learned about last time already. Let's see what's happening here. So this shows the effect of solar radiation and the effect of wind, but nothing more. So the interaction is not shown here, and we can also see that there is an error message here. Model appears to involve interactions. See the help page. So there seems to be something happening here which does not allow us to directly use the termplot function in order to interpret the model. So what we have to do now is, in order to predict from the model, we have to use specific ranges of our explanatory variables when we want to interpret the interaction between solar radiation and wind. So let's do that quickly. First of all, let's look at the summary of solar radiation within the air quality dataset. The summary shows us that the minimum of solar radiation is 7, the maximum is 334, and there's some missing values in there. So we use the summary here, put hashes before the outputs, and now let's think of what we want to do. Let's say we are interested in the effects of wind on ozone, but we want to see how solar radiation changes this relationship. So we want to plot the interaction among these variables. For this, we need to decide on particular levels of solar radiation for which we want to produce predicted values of wind speed. So let's do that. Let's create some particular values of solar radiation that interest us. Let's call this solar1 equals mean air quality $solar.R na.remove equals true. So solar1 will be the mean of solar radiation, and you will see in a second why we need that. Okay, and let's use another one. This will not be the mean of solar radiation. Let's use maybe the first quantile or something like that. Let's just use 100, and then the next line maybe a bit higher value. Solar3 shall be 300. Okay, so what we'll have now is we have just created 3 values of solar radiation. The first one being the mean, 185. The second one being the first quantile, around 100. And the third one being somewhere close to the third quantile or the maximum. Okay, anyway, we just produced these values, and now we need to produce predictions from our model. So we use the predict command like this. If we just say predict model 2 to start with, we will get predictions for all values of solar radiation in the model and for all values of wind speed in the model, combined to a single prediction of ozone here. So basically, this predict function gives us, for the 153 data points in the dataset, the predict function will just give us the predicted ozone levels here. That's not what we want. We want to have particular predictions. Let's make it very easy and start with just 2 particular combinations of wind and solar radiation. So predict model 2, comma, data.frame solar.radiation equals 100. Let's say we want to have a prediction for 100 solar radiation, and wind equals, well, what should we put in here? We need to summarize also the wind speed. Let's produce this summary also here. So summary air quality wind. So the summary will show that the maximum speed is about 20 and the minimum is about 1. So let's produce a particular prediction here for a solar radiation of 100 and a wind speed of 10, maybe 10 miles per hour. Okay, so, and we need to close the brackets. Control R, and this is the predicted ozone concentration for this combination of values. That's not what we want in the end. So let's use our particular values of solar radiation that we just created. Copy this line again, and we say solar radiation equals solar1. We know that solar1 is the mean of solar radiation. Send this line over and we get another predicted value here. So the predicted value is 41 ozone concentration here. So what are the units, by the way? What are the units of these measurements? We can use question mark air quality to get a feeling of what these values mean. So a new window will pop up here, and you can see that basically the ozone concentration is given in parts per billion, solar radiation is given in a specific unit here, Langmuir units, and wind speed is given in miles per hour. Okay, let's go back to our predictions here. So we predicted now for the mean value of solar radiation and for one particular wind speed. Let's formulate predictions for a whole sequence of wind speeds ranging from 1 to 20. 1 to 20. You will see what happens now. We get predictions now for average solar radiation and for a whole range of wind speeds. There you go. You get these 20 values here, and these will be the predicted ozone concentrations. You can see that something strange happens here. So we can get even ozone concentrations smaller than 0, given that the solar radiation is at its mean. This indicates again that potentially modeling these data could be more difficult than we anticipated in the beginning. Anyway, let's call these predictions P1. These are the predictions for average solar radiation. And we just copy this line here and produce predictions for the other levels of solar radiation, P2, P3. So the first prediction will be for average solar radiation. The second one will be for solar radiation of 100 units here. And the second one will be for solar radiation of 300 units. Okay, so we have 3 lines of code now, P1, P2, P3. These differ only in this respect, so it's always the same range of wind speeds, but it's solar1, solar2, or solar3 now as levels or ranges of that variable here. Okay, and we have to type P3 here, as I just say. Okay, let's run these lines, and we need to, just saw that I didn't run these ones here, so I need to run these 3 lines and those 3 lines. And there you go, we have these predictions here. P1 is for average solar radiation. P2 is for, let's say, bit lower solar radiation, and P3 is for a very high solar radiation. And you can see that the levels of ozone predicted here differ considerably. So this is for almost no wind speed here. No wind speed, but mean solar radiation gives us 90, and low wind speed and low solar radiation gives us 63. Low wind speed and high solar radiation gives us 100. It's much easier to visualize these predictions using a graph now. So let's plot the relationship among ozone and wind. And the data set is air quality. Let's do that. This shows us this graph here. And now let's fill in the predictions lines. So we need to use the particular values of wind speed that we used in order to create the predictions. So which are these values? You can find them up here. We used wind speeds from 1 to 20. So that's what we need here, 1 to 20, comma, P1, brackets closed. What's happening now? So this line here shows us the relationship between ozone and wind for average solar radiation. Average solar radiation is this mean value somewhere up here. There you go, it's about 105 units here. Okay, so let's produce the next line of predicted values here, which will be for P2, for the low solar radiation. Now you can see that the slope has dropped now. The slope of the relationship among ozone and wind has dropped now. And finally, let's produce the last line of predictions here for P3. And this shows that the line has increased in slope. The slope of the line has increased. What you can see now is basically what the model has done. The model has produced us a prediction indicating that there is an interaction between wind and solar radiation. And what you can see is that the relationship between ozone and wind differs and depends on the levels of solar radiation. So solar radiation has an influence on this relationship. And whenever we have interactions among continuous variables in multiple regression, we'll have to use these methods in order to delve deeper into the relationships in our data. Now, to summarize, what we've done today is we've fitted a multiple regression model with interaction, and we've plotted the predicted lines for certain levels of one of the explanatory variables. And that's what we're always going to do when we have interactions among continuous variables. We choose particular values of one of the variables and let the other variable vary across its whole range. And in doing that, we are able to inspect graphically relationships among interacting continuous variables. In the next videos, we will discuss in greater detail problems arising in multiple regression, these problems being interactions between more than two variables and variance heterogeneity and the effects of centering on multiple regression situations. For now, I thank you very much for listening, and I hope to see you again soon in one of the next videos. Bye bye.